So, you are pretty comfortable with exponential functions. Here's one, y equals 2 to the x. And you know, if you put in x equals something, you can get out of y equals something. If x equals 1, you get 2 to the 1, which is 2. If x equals 2, you get 2 to the 2, which is 4. And you can put in fractional numbers here. You can even put in x equals 0. You get 2 to the 0, which equals 1. You can put in negative numbers. X equals minus 1, and you get 2 to the minus 1, which is 1 over 2 to the 1, which is 1/2. So you can get smaller numbers. Notice you never get a negative number out of these. If you look at the exponential function, it looks something like this. It goes through the point 0, 1, and then it just takes off that way. But it approaches the x-axis asymptotically. It's closer and closer, but it never gets there. I mean, you never get any negative numbers out. Well, right. You never get any negative y values. Well, let's talk about inverses. Remember inverse functions? We haven't talked about them much in polynomials because they can be difficult to deal with there. So we kind of give them a pass. They're not as important. They are vitally important, however, in exponential functions. Remember, if you take an inverse of a function, you compose it with its inverse, you get back the original function. Well, there's an inverse to exponential functions, and we call that a logarithmic function. So the inverse of this function is y equals log base 2 of x. Alright, that means if we compose these two functions, they're different functions. If we compose them, we get back x, and we can compose them either way. So that means that log base 2 of, and wherever we see x, we put in the other function, 2 to the x, this equals x. Also, if we take 2, and we raise it to the power of log base 2 of x. We take the function 2 to the x, and wherever we see x, we put in the other function. This also equals x. So you can think of log base 2 undoing 2 to the x, and 2 to the x undoing log base 2. And basically you just go backwards in these. So if we had log base 2 of 2, we're going backwards, so we find out what number we have to raise 2 to the power of to get 2. And for that, it's going to be equal to 1. Log base 2 of 4, we're saying what number we have to raise 2 to. 2 to the what equals 4. This is how we're undoing it. And we know 2 to the 2 equals 4. Okay. Log base 2 of 1/2. What number do we have to raise 2 to get 1/2? Well, here it's minus 1. This equals minus 1. So basically, it is an inverse function. This goes through the point 0, 1. This goes through the point 1, 0. And it looks like that. Okay. Very straightforward. You can apply this to either side of an equation, just as you can add and subtract things to each side. You can multiply each side by things. You can raise things to the power and take the log of both sides. So if I had the function 2 to the x equals 8, well, or this is an equation, and we want to solve for x, we can take the log of both sides. We want to take the log base 2 of both sides, because that'll get rid of the 2 to the x. So if I have log base 2 of x, 2 to the x, I'll put a brackets here just to make that clear. That's the same as log base 2 of 8. Alright, log base 2 of 2 to the x. These two functions are inverses, so they cancel each other out. When you compose inverses, you get back the original x values. So that's another way to write that. 8 is just 2 to the, let's see, 2 to the 3. Log base 2 of 2 to the 3. And you know, log base 2 and 2 to the power of our inverse function, so this ends up being 3. That's sort of one way to do it. I mean, you could have looked at this and said, yeah, x 2 to the x 2 to the 3 equals x. But this shows you how these composition of functions work. I'll do another example. But these are pretty straightforward. Just know that log is asking you to take the inverse. Let me clear this out. Say you had, I'm using log base 2 a lot because it's pretty straightforward what's happening. Equals k. Suppose we had this equation. We wanted to know what k was. Well, we can raise both sides to the 2. Take 2 and raise it to that. Take the equation and use that as the exponent for 2 for each. These are inverse functions. 2 to the log base 2 of 32 ends up being just 32. And this equals 2 to the k. Maybe that's a little easier to look at. We say 2 to the what equals 32. Let's see, 2 to 1 is 2, 4, 8, 16, 32. That equals 2 to the 5th. So here we see k equals 5. Okay, we rarely deal with log base 2 once we get out of getting our sea legs for how logs work. But if you have 10 to the x, the inverse for this function is the common log, just the word log, 10 to the x. So if you have log 10 to the 2, these are inverse functions, and it just ends up being 2. Similarly, if you have 10 to the log base 3.7, believe me, that's 7. These are inverse functions, that ends up just being 3.7. So, inverse functions, undo them. If you had an equation which had log in it, you could raise both sides to the 10 power to get rid of the log. Notice that you do have to raise the whole side of the equation to the power. Say you had 2 times log base 10 of 4 equals x, and you want to raise both sides to the 10 to get rid of the log. You have to do it to the whole thing, so it's 2 times log 4 equals 10 to the x. Okay, so you can use your rules for exponents to separate this out. Okay, we'll do that in a later problem. That's pretty straightforward. Now that we're getting comfortable, once we start to get comfortable with logs, try a few problems. We will be dealing a lot with y equals e to the x and its inverse, y equals natural log of x. This is ln, your old friend ln. You'll see it on your calculator. I think it's backwards because it's French, so they put the adjective on the back. It's log natural, or something like that. Alright, undoing logarithms are just inverse functions of exponentials. It's a weird word. It doesn't sound like It's the inverse, but it is. So we'll try a few problems with these. These are pretty straightforward.